Okay, so we'll move on in chapter 18, focusing on multiple substituents. And we need to understand the directing effects as discussed on many slides before this. When we have more than one substituent, we need to look at all of them and classify them and understand the electronics in these EAS reactions, electrophilic aromatic substitution reactions. When we have a molecule like this, we have a directing effect of the methyl group, the R group, which only has a slightly has a weaker effect through induction. And then we have the NO2 group with a stronger effect through resonance, induction and resonance. As we are looking at this potential reaction here, if we want to figure out where the bromine atom would end up, we actually find that when we have the para arrangement of an ortho-para director and a meta director, that this actually favors this position here, the ortho position to the methyl group, the meta position to the nitro group. Of course, there's symmetry, so here's another position. And so bromine will go ortho to the CH3 group and meta to the NO2 group. So these are kind of these two groups, because the electronics are acting in concert to favor just one product. So that's a good situation. If the groups direct to different carbons, then we have to really focus on which one is stronger. We have learned that resonance is a much stronger effect than induction, and that will then prevail. For example, here we have an ortho-para director through induction, and here we have an ortho-para director through resonance. Remember, we have electrons that could be put into the ring, which is much stronger through the resonance effect compared to the induction effect here. So for a net addition of NO2 to the structure, with NO2 plus being our electrophile, E plus, which we have often used as a placeholder, we now have to prioritize which one is going to have the stronger effect. Of course, it's going to be this one. So this will prevail. The para position is already blocked. So here we are, and we get this product. Again, you may want to integrate some examples here into your notes so that you can quickly review as we move on to the two other chapters in the semester. We also need to pay attention to steric hindrance. Steric hindrance has to do with if a substituent is very bulky, big, occupies a lot of space, that will have an effect. For monosubstituted ring, especially when we have an alkyl group, such as an isopropyl, maybe a tributyl, we will have the para addition as the major product. And this only as a minor product because, remember, there are methyl groups attached here that are not so obvious when we have a skeletal drawing as shown in the slide. But that is going to obscure this position more, so sterically the para position is favored. Moving on. If we have 1,4 di-substituted rings, substitution will occur at the less sterically hindered site. So now we are pitching two alkyl groups, R here and another R over here. But of course the methyl group is much smaller than the isopropyl group here. So as we do our net addition of nitration for NO2 addition, so HNO3 in the presence of an acid catalyst, here the sulfuric acid generates NO2 plus as the electrophile. We now see that the ortho position of the less sterically hindering R group is going to be favored. So that's going to be your major. Okay. Why? Because again, we have a lot more space occupied by this isopropyl group here. And sometimes this, you can see this is indicated, so this is bulky, so these groups would run into each other. So that's why this one here is preferred. On the next slide, we're now talking about 1,3 di-substituted rings. So as we're looking at this, we typically do not see substitution between the two substituents. So see how there's more crowding in this position because of the isopropyl group here and the methyl group here. So it's more likely to now see that an ortho position favored by either one of these two inductively electron donating groups, we would have possibly this product here, ortho to the methyl group and ortho to the isopropyl group. But because isopropyl is much bigger, again, and we can draw these brackets indicating that because of their bulkiness, they kind of run into each other, and that this position in between the two substituents is not observed. So I highly recommend that you practice with all the skill builder sections in your book. And again, the more you move your pencil, the better you'll do. And I kind of pasted in, here are 1, 2, and then 3 and 4 examples of how to practice after you work through the skill builder, where it takes you through step 1 and 2 and gives some explanations as to how you deduce the answer. And again, you do not want to just memorize structures. You want to be able to have a logical conclusion to the whole analytical thought process to derive a good answer. So let's move on to the next slide. Here, this is a rather different concept here. So now in this section, we are talking about blocking groups. Remember how we have looked at different effects of the groups, and now to make this very practical, we want to understand how we can control substitution patterns. So consider how one might force a substitution to add ortho instead of para in the presence of an ortho-para director. How would we do that? So this is where we can actually bring in a blocking group. So here we are, blocking group, in order to prevent, if we wanted to have an ortho or 1,2 substitution, where the bulky alkyl group with inductive positive activating effect is present, we had said that the para position would be favored. But if we introduce something in the para position to then force the halogen into the ortho position, that would be an easy way for manipulating the outcomes. So a blocking group could be used to prevent substitution in the para position. We install the blocking group. It's just here like a placeholder. Then we brominate, and then we remove the blocking group. How do we do this? Well, when we discussed the sulfonation reaction, we learned that there's a forward and a backward reaction. If we have concentrated fuming acid, so this meant that there is SO3 enriched in the reaction mixture. It's an SO3 addition. We get the sulfonic acid, which is electron withdrawing, has its own effects. But if we dilute that, we can go back and get rid of this. So this SO3H group is a very good blocking group. So we can now accomplish our goal. If we want to go from here to this product, we're going to have to take a couple of extra steps. We first introduce this that's going to block the para position. We then do the halogenation, which is a net Br plus addition, replacing the hydrogen with the bromine. And then we dilute the solution. If it's all done in one pot, we just add water. But the bottom line here is that we can now remove the blocking group in this step. And we have a lot more control with this, and you can practice this with Skill Builder 18.4. So now we have actually many synthetic tools to manipulate the functional groups on aromatic rings. So here we are. There are 10 different groups that we can install on the benzene ring. We had seen this before, right? Bromo, chloro, nitro, sulfonic acid, or after a sulfonation reaction, alkyl groups and acyl groups. And we had seen that we can even go a couple of steps further. We go from a nitro group to an amine group. This is aniline. We can also go from a methyl group to now halogenation. If we were to use excess NBS, we could get CBr3, and there will be additional chemistry possible with some of this, but we can also use oxidative procedures. In this case, the methyl group here would be fully oxidized. We go from 3 carbon-hydrogen bonds to 3 carbon-oxygen bonds in the form of a carboxylic acid. And we can also, in order to prevent some of the side reactions, all the drawbacks of a Friedel-Crafts alkylation as shown here, going to the Friedel-Crafts acylation that has a lot more control, but ultimately then reducing the acyl group to get an alkyl group without many of the side effects and distracting aspects of Friedel-Crafts alkylation, as discussed before. On this slide, some more information about synthetic strategies. Dye-substituted benzene rings require careful analysis of the directing effects to decide which group to install first, because there's a electronic effect that's going to play an important role for when the second substituent comes in. So groups need to be META in this case, and so the first group installed must be a META director, unless we take a detour, but let's just go with this example here. Which one of these is a META director? We had learned that the nitro group is actually the stronger META director. So, and Br is our Jekyll-Hyde group. It's deactivating but orthopara directing. So we're going to have to start with the nitro group and then add the bromine. You also have a nice chart for overview, table 18.2. that now discusses a lot of the synthetic aspects. Synthesis is all about functionalizing, figuring out what the toolbox is for now installing functional groups. And you can pause the video here and just review all of the groups and review your knowledge of all the rules that helped us understand what the role is of the first substituent and where it will direct the next substituent. Okay. The other thing we see here is that some of the additional conversions that are possible, so nitro group can be META directing, but if we ultimately want to turn it into an amino group, we can also take advantage of the fact that this now has different directing properties, right? Again, what was shown just before in the scheme. Here we have a methyl group, which is a moderate orthopara director. But if we oxidize it up to the carboxylic acid, here we have the multiple bond. Now we see that this is a META director, so we can take advantage of this. And then here we have another example, the reduction of this an electron withdrawing group to an electron donating group, and then here the same thing over again. This is where our understanding of electronic placement and their effects will be very powerful to help us with mechanisms and overall reaction outcomes. Along the lines of synthetic strategies, here are some additional considerations. So groups need to be meta, but both of these are ortho-para directors. So what are our options? We use a little detour. So remember that the amino group requires nitration, then reduction. We could actually introduce the nitro group here and then reduce it, and we're changing now the electronic nature of the ring, and therefore we can control the position of the next substituent. Okay. So we take advantage of the meta-directing ability of the nitro group before reducing it to the amino group. And so here's your synthetic sequence. You do a nitration first, then a halogenation, and then the nitro group would be in a two-step procedure reduced to the amino group, the aniline derivative in this molecule. Other limitations that must be considered when planning a synthesis are nitration cannot be done on a ring that already contains an amino group. So there are some side reactions, and so please make a note of this because there are some other reactions that can take place. And in the next slide here, Friedel-Crafts reactions do not work on a ring that is moderately or strongly deactivated. If you have a carbonyl group here, multiple bond, right? Here, multiple bond and a positive charge on the nitrogen. These are not reactive enough. And then I encourage you to practice some more with these skill builder examples.